Alright, so guys, the calculations we've done or did yesterday all solved for the amount of energy or the amount of heat needed to accomplish some process. So we calculated the amount of heat required to melt ice, or the amount of heat required to heat up 10 grams of water by 10 degrees, or to do some combination of those two things. But either way, we were just solving for Q, so heat or heat energy. What you think about today is all the heat that is used to do those things, to melt the ice, to heat the water, whatever it might be, had to come from somewhere. Right? We can't just produce energy spontaneously. So today we want to think about where that energy comes from, how we can account for that, and how that can help us with calculations. So before we do that, let's talk really quickly about the calculations from yesterday. All the calculations yesterday involved an increase in energy, or an increase in temperature, or a phase change, solid to liquid, liquid to gas. So everything we did, energy was increasing. Could we do the exact same calculations in the opposite direction? We cool water by 10 degrees. We freeze water, or we condense water. Yeah. So we'll get the same answer, the same amount of energy change happens, but if we heat by 10 degrees, we add energy. If we cool by the same 10 degrees, we release that energy, okay? So we would have the same numerical value for Q, just a different sign there. Okay, so be aware, just because we've only done heating and phase changes towards gas, the exact same things happen in the opposite direction. So if we think about for a minute, if you take an ice cube and you hold it in your hand, what's the ice cube going to do? It's going to melt. So there's going to be some energy associated with that phase change, right? Where is that energy coming from? Your hand, right? So the energy absorbed by the ice cube will melt it. Will your hand undergo a phase change? No. Will your hand undergo a temperature change though? Yes. So will the energy changes be different? Will the energy lost by your hand equal the energy gained by the ice cube? For the most part, yeah, assuming we don't lose any energy. But the ice cube won't necessarily increase to the temperature of your hand, right? Because we have to first account for a phase change that requires energy. So that's not a great example because your hand will eventually warm back up because your body is producing heat. So let's think about an example of a little piece of metal. If we take a metal block and we heat it up really hot and we drop it in water that's cold, the temperature of the block is going to do what? Go up or go down? It's going to go down. The temperature of the water, though, is going to do what? It's going to go up. Eventually, the two temperatures will become equal, right? So if we take a 100-degree block and drop it in a 50-degree bucket of water, will the temperature become 75? Not necessarily, right? There's a couple of things that depend or determine that. So the mass is a big factor too. If you think about dropping a hot penny in a 55-gallon drum full of water, is it going to make a huge change in temperature? No. But if you drop a hot bowling ball in a 5-gallon bucket, then it will make a larger temperature change, right? You also need to think about the specific heat of these substances. So the specific heat, or heat capacity, is how much energy is required to heat 1 gram by 1 degree. So some things heat up more easily, okay? So water versus copper, for example, one of them, it might be easier to have a change in temperature there. So we must consider that. But in a simple way, we can say that Q, which stands for what? We can just say heat or heat energy. So we'll say heat gained, because that's really all we've calculated so far. We've calculated heat gain during a melting, heat gain during vaporization, heat gain when temperature goes up. So all our calculations, we've really just calculated how much heat do I gain. So the heat that we gain has to be lost from somewhere else, right? So I could also say the heat gain equals the heat lost. Does that make sense? Hopefully, it's pretty logical. Whatever energy or heat we gain, we got to get it from somewhere. Okay. So overall, we don't have a change, but we do have a transfer here. So the calculations we're going to look at today, and primarily, are not going to involve phase changes. They're only going to involve temperature changes. So if you think about the simple example of dropping the metal cube in water, will I see a phase change there? No, I just see a temperature change, right? So if I am only calculating heat only during a temperature change without having a phase change, is there a single equation that I can use to do that? Yeah, and what is that? Yeah, MC delta T. So I can say Q equals MC delta T. So I'm just substituting in, because does Q equal MC delta T? Yes, I can substitute that. So I can say MC delta T equals MC delta T. So heat lost equals heat gained. So it's pretty common to see one of these with a negative sign in front of it. So if you see that, we'll talk about why. We probably won't worry about that much. If you put something hot into something cold, one of the temperatures will go up, right? And one will go down. If the temperature increases, is delta T positive or negative? Positive. If temperature decreases, is delta T positive or negative? Negative. So one of the Q's will always be negative. We won't worry so much about that for now. We'll just assign the correct sign, plus or minus, when we get done. So mass will always have what sign, positive or negative? Positive. Specific heat will always be positive. Okay. And then delta T can be either positive or negative. Temperature can increase or decrease. So one major issue with using this, if I say the heat gained by the water, for example, is equal to the heat lost by the metal, that assumes that all of the energy is perfectly contained. Okay? So if I drop a hot piece of metal into cold water, is the air above the water also going to get hot or get warm? Yeah, so I'm going to lose some energy there, right? Will the container that it's in also get a little bit warmer? Yeah. So will this equation always work perfectly? No, because it can't account for all the ways that we lose heat and lose energy. So we're assuming we're in a perfectly insulated system. So it's very insulated, it's very isolated, so no heat can come in or out. So in this case, we could say the heat lost by the metal, going back to the metal block in water example, is equal to the heat gained by the water. So we know that there is a specific, I can't say that word, specific C value for every material. Water in the liquid state is 4.18 joules per gram degree Celsius. So if I had a big table of all the different metals, I could use this formula to figure out the identity of the metal. So if you think about the metal block in the water example, is it easy to find the mass of the water? Yeah, you can weigh the water, right? C, do I know the C value for water? Yes, 4.18. Can I easily find the delta T for the water? Yeah, measure the temperature before I drop the block in, measure the temperature after I drop the block in. So that's pretty easy. Could I find the mass of the block pretty easily? Hopefully, put on the balance. Then could I find the delta T for the block? Yeah, the temperature before and after it goes in the water. So then if I know MC and delta T, and M and delta T, could I solve for the C value for the metal? Yeah, and that is a constant for different metals. So I could go to the chart and match it up. Is it copper, is it aluminum, is it iron? The one issue with that is they don't really work for alloys. So what are alloys again? Yeah, a mixture of metals. So alloys can exist in different ratios, so the specific heat can vary slightly for those. So it works best for pure metals. So if I have my delta T, I can measure the initial temperature of the water, the initial temperature of the metal, do I have to measure the final temperature for both the block and the metal? Now they're going to be the same, right? So you can make a note of that. We'll assume the final temperature is going to be the same. Okay? So if you put the metal block in the cold water, the heat and energy will transfer until their temperatures are equal. Okay, so a lot of questions will say the final temperature is this, and it just gives you one number. That's because it's the same for the block and for the water. Okay? So this process of dealing with where the energy comes from, when it's lost or gained, and using that for calculations, we call it calorimetry. And so we'll talk about that more in a little while, different forms of it. But for now, let's look at some of these calculations just with a simple example of the metal block in the water. So the first example says a metal with a mass of 8.3 grams is heated to 87.3 degrees Celsius and, I should say, then dropped in a cup of water with a mass at 21.4 degrees Celsius. The final temperature of the system is 26.0. What is the specific heat of the metal? And it gives you the C value for water. So I'm going to rewrite this. I'm going to write 123.0 grams of water is heated from the initial temperature of the water is 21.4 to 26 degrees Celsius. So when it says the final temperature of the system, what does that mean?
No reaction.
There's no reaction. The whole thing, right? The metal plus the water. So the system refers to everything. So the metal and the water temperature is that. So that's a question from yesterday. 123 grams of water is heated from 21.4 to 26 degrees Celsius. Could you find how much heat is required to do that? Yeah, so do that. So phrase it, how much heat is required to raise the temperature of 123 grams of water from 21.4 to 26. So I can say Q gained by water equals MC delta T. So 123.0 grams. And it gives you the 4.18 in the problem. If it hadn't given it to you, it's in the table in the notes. 4.18 joules per gram degrees Celsius times, what is the delta T from 21.4 to 26? 4.6. So there's only one unit that does not cancel. What is that unit? Heat's not a unit. Joules. There you go. So is that a valid unit for what I'm trying to calculate? Yeah, so we're in good shape. So I wrote the number down just so you can have an example, but in the future we won't write this number down. Okay, we'll kind of simplify it. But for now, write the number down. So the water gained 2,365.044 joules of energy. So where did that energy come from? Block. It's not a trick question. The energy gained by the water came from the hot block. So could I say this number, so 2,365.044 joules equals Q lost by metal? Is that a true statement? Yeah. That's assuming there's no energy lost to the air. That's okay. So can I now use Q equals MC delta T of the metal? Yeah. So what was the mass of the metal block? What was it? 8.3? Do I know the C value for the block? No. So what is the delta T for the block? 61.3. Somebody agree? You said it's hesitant. Yeah. Does it go up or down? It goes down. Okay. So if we put a negative here, we can just put a negative in front of the heat loss so that it cancel out. We can just leave the negative sign off though. So now when I do this, when I divide this number by 8.3 to solve, does joules over gram cancel? No. Does joule over degree Celsius cancel? No. So it's going to have some odd units. So type it in and see what you get. Solve for C. And you can just leave that term out. So I know in the problem I gave you units of joule per gram degree Celsius, so you can be confident that's correct. But don't just assume C will have units of joules per gram degree Celsius. I actually plug the units in C. The numerator can be any unit of energy, it could be calories. The denominator could be any amount times any temperature, it could be moles per degree Fahrenheit. So make sure you cancel your units and verify what they are there. So now if I had a big long, just a second, if I had a big long list of elements and compounds and their C values, could I match up and figure out what this is? Potentially, yeah. Yeah.
So the equation always works as long as the units match, no matter what units they are?
Yep. Okay. So here, I did MC delta T, got a number, and set it equal to MC delta T. Do I have to calculate this intermediate value? No. Is it okay to just do this? Could I have done MC delta T equals MC delta T and done water and metal block and just done it all on my calculator? Is that probably a better route to go? Yeah, there's a fewer places to mess up. It's easy to mess up going from calculator to paper and back and forth. I would just do it like this. Plug in 123, 4.18, 4.6, 8.3, C, then 61.3, then just solve for it that way. And that's a much easier method for doing it. So, guys at home, before I turn this video off, work on the rest of them on the front and back. If you have issues with number 3, skip that one and come back to it. Number 3 is labeled challenge, a little bit harder. Go to the ones on the back. Those should be easier. 4, 5, 6, and 7, and then 8 also will be a little bit harder. Okay. So if you have any questions, send me an email and I'll help you out. So guys, here, go ahead and work on question number 1 and 2.